Let's now take a look at a numerical example. Now, in all these lectures, we will be looking at numerical examples that are very small. The reason we look at small example is that we want to spell out almost every step of the computation, even though it might be just an addition or multiplication, because we want to avoid any symbol phobia on the minds of some students. There's nothing mysterious about the symbols. Once you see them in action with numerical values, then you may feel a lot more comfortable with the symbolic operation. But in order to show the numerical addition multiplication within a slide or a page of the textbook, we have to stick to small dimensions. Now, in many cases, that actually does not capture a key difficulty in the challenge. That is the challenge of scale. Okay, so we will not be able to demonstrate why the problem is difficult because it has to scale up. Now, in this case, it turns out that usually the scale of a single cell is not that great. Okay, but still, we're talking about, in this case, a 4-user cell, which is a lot smaller than any typical cellular traffic that you can expect. Now, having said that, the advantage of small examples is that we can write out every step in the textbook or during the lecture. So here is the Gij values captured in a 4x4 tables. Okay, there are 4 users. And we're going to make up some number that will make our computation very easy. We say the diagonal entries, which are the G11s, G22, G233, and G44, they're all the same, which is 1. Okay? And then the Gijs are smaller because of the help of spreading code for the GIIs. And G12 in general may not be equal to G21. Okay, so this is G12, this is G21. All right, now these are the given parameters depicting the channel conditions for both the direct channels and the interference channels. Now, what about the target gammas? I'm going to say that gamma 1 is 2, gamma 2 is 2.5, gamma 3 is 1.5, and gamma 4 is 2. It turns out this set of gamma target SIRs is indeed achievable. And remember, the gammas are unitless numbers because it's the ratio. And then the noise levels, the NIs, are all equal to 0.1 in the units of milliwatts. So that's the set of constants. And now let's take a look at what would happen to the transmit power vector over discrete time slots from initialization at time 0 forward. Now, of course, in a real system, there's mobility. So you don't even have the same constant number of users. In a real system, the channel may also change before your algorithm can converge. We're skipping those important details in practice just to focus on a simple example to illustrate the dynamics of convergence of the p-vector.